This episode is brought to you by GPRS. Construction professionals know that utilities and concrete reinforcements can cause big problems when you're on the job. GPRS helps you avoid them. We use ground-penetrating radar to detect rebar, conduit, and post-tension cables before you cut, core, or drill. And our concrete scans are 99.8% accurate. We guarantee it, helping you reduce hits, downtime, expenses, and keep your people safe. To keep your job site safer, visit gprsinc.com. This episode is brought to you by Concrete Logic Academy. If you work in concrete, engineering, construction, or ready mix, you already know most of what matters isn't taught in school. That's exactly why we built the Concrete Logic Academy Unlimited Pro membership. You get unlimited access to 25 concrete courses, plus real-world breakdowns, research, and a community of professionals solving the same problems you are. Instead of paying for one course at a time, you get the entire library in one place, built for how you actually work. No travel, no hotel ballrooms, no sales pitches, just practical concrete knowledge you can use on your next project. Start your free trial at www.concretelogicpodcast.com/pro. If you're a ready mix producer and you've been trying to figure out how to actually train your team, this is for you. We built the Concrete Supplier Playbook Foundations inside the Concrete Logic Academy specifically for producers that want their people to better understand the concrete they're selling and supporting. It's simple, on-demand training your team can work through at their own pace and start using right away. For podcast listeners, we quietly opened up a limited Founding 300 group. If you want to see what it's about, go to concretelogicpodcast.com/founding300.
What's the most used man-made material on Earth? I'll give you the answer. Concrete. This is the Concrete Logic Podcast. Have you ever stopped to think about the sidewalks, driveways, bridges, or the buildings around you? They're all made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore a unique concrete-related topic with the help of industry professionals shaping the trade's future. We'll talk with suppliers, contractors, architects, engineers, specialists, and even proponents of competing materials. We'll get their views on concrete and their visions for its future. So get ready to mix things up with Concrete Logic, where we turn the spotlight on the material that's everywhere but often overlooked. This is the Concrete Logic Podcast. And now, here's your host, Seth Tandit.
And welcome to another episode of the Concrete Logic Podcast. And we have Bob Higgins back with us. Bob's been in the concrete industry for decades. He's worked across the cement chemistry, admixtures, durability, and performance. If you've been listening to the podcast for any length of time, I'm sure you've ran across Concrete Bob's episodes. There's quite a few. Today, he's joining us. We're going to talk about alkalinity, the pH environment inside concrete, and the lever or levers that controls durability for concrete. So if you don't understand alkalinity, stick with us. You will by the end of this episode. But before we get into the topic at hand, just want to remind you guys how to support the podcast. So if you go to www.concretelogicpodcast.com, on the homepage, there is a link at the top that says Ask Seth. If you click on Ask Seth link, that's a way to get a hold of me. And what I'm looking from you is topic or guest suggestions that you want to hear on the podcast. So please reach out and do that. If you want to leave me a voicemail, on the bottom right-hand corner of that same homepage, you click on the little microphone and you can leave me a voicemail. The second way is on the same homepage, there is a donate button. If you click on donate, it allows you to give any amount to the podcast. And if you get any value from the show, please share some value back. It's kind of what it is. And I'm not going to tell you what amount that is, or there's no dollar amount when you click on that link. It's for you to determine what you get out of the show. So please donate if you do get value out of the show. The second or the third thing, I'm on the third thing now. The third thing you can do is check out Concrete Logic Academy.com. There's links on the podcast website that you can click on, but you can also go to www.concretelogicacademy.com. And if you enjoy the format of the podcast, we do the same thing on the Academy, but we give you quizzes and some other extra things within the Academy that helps you absorb the content that we're talking about. Okay, Bob, we're back. And just behind the scenes, this is take 2. We lost internet, so we're back. We're going to try this again. Bob, just to get you warmed up on the subject at hand, when we say alkalinity in concrete, what are we actually talking about?
Alkalinity is actually the concentration of a salt. It's an alkaline salt. There's a lot of different salts that are out there, and I'm going to give a background on what salts do and how they affect moisture, not only moisture that's available to concrete for hydration, but just moisture in general, how it affects it. And once people understand what they're dealing with, a lot of the mysterious problems they're running across, be able to figure it out.
So is this the root cause of all the problems? And when we say problems, what kind of problems are we talking about?
It is one of the root causes. Because alkalinity, unfortunately, people get high pH and high alkalinity mixed together. And I keep reading study after study, and they keep doing that. So no wonder people are confused. They say, well, we have a lower pH concrete. No, it's a lower alkalinity concrete. The pH is the same. But if you notice, when you read studies like that, they won't give you the pH because it's the same, but they don't know why. So they just use the term pH. But the biggest issue that we have with alkaline salts is its ability to grab and hold on to moisture. And that is really, really critical during the curing phase of concrete. So I'm going to just go back and just give some basics on salts. All salts will reduce relative humidity, some more than others. And the ones that are consistent are the ones that are used as calibration salts, where they have basically 4 different salts that they use in these little containers that are full of water, because no matter how much water's in there, if it's saturated, it will maintain a consistent relative humidity through a very broad range of temperatures, because temperature will also affect the alkalinity and the ability of these different salts to hang on to water. Because a lot of mistaken belief is the water, once it's hung on to, well, it's chemically bound. Well, no, it's not, because it can be taken on and released in normal, everyday climate. So that is not bound water. They keep mix and matching these terms to where even the experts get confused. So I'm going to get into the most critical alkaline salts that are in concrete. Your 2 most critical alkaline salts in concrete are calcium hydroxide and sodium hydroxide. I've heard people say potassium hydroxide, but that's kind of interchangeable with sodium hydroxide because their response to a moisture is almost identical. There's very little to separate them. So I'm just going to focus in on sodium hydroxide so it doesn't get overly complicated. Because one of the things is when they started adding cement kiln dust to cement between 2002 and 2018, that didn't change the pH as much as it changed the alkalinity. And that's where that kind of slid in under the radar. And that's one of the problems that we're seeing, because as the alkalinity increased, it also increased the setting of the cement. It also made moisture less available to creation of cement. So I'm going to go into the background of salts. Again, all salts will reduce relative humidity, even if the moisture hasn't changed at all. It can remain the same. It's like sodium chloride, table salt. Table salt is available anywhere. And one of the examples I give people is it can create a condition where it will take water and hang on to it. even though it's not at dew point, it can actually create condensation. So that's called ionic dew point. So that condensation can be captured and can cause issues in the concrete, because now with it capturing the water, that's no longer available for the cement. So in the little tabletop example I gave is I'll take just table salt and I put it in a little container, and it's dry and it's 70% relative humidity. Then I put a cap on it and I raise the humidity to 80%. And even though it's not even close to 100% relative humidity, which normal atmospheric condensation will occur, dew point, it will begin to liquefy and it turns into a liquid at 80% relative humidity. So that water is now captured. That's not available to be measured, because as you put something down on there, like a relative humidity probe or anything like that, it will measure 75% relative humidity. According to some experts, that's supposedly dry. Well, it can be saturated, but it's measuring dry because they misinterpreted what the salts do. Now, here's where the alkaline salts...
Hold up. I'm going to pause you. So the moisture's in the salt.
Yeah, it's captured to a certain extent.
In the salt, so it's holding on to the salt, and that's why you're saying if you use a RH meter, it's not capturing what's going on in the salt, just what's going on
in the airspace. Yes,
in the airspace, right?
That's all it's measuring is the airspace. So there can be a whole bunch of water in there, and the RH will not see it. It can't see liquid water. None of them can.
Okay.
That's beyond its capability. Now, when you have a lower RH, that also equates to a slower evaporation rate. So things like the calcium chloride test, because it's fixed at 60 to 72 hours, there's only so much moisture it can capture in that kind of a climate versus an open system where it can readily capture moisture and will give you an accurate reading, especially now with the cement kiln dust in there. And now with the changes in concrete, that's no longer a viable way of measuring moisture content. RH and calcium chloride are not viable. And here's why. Because there was one famous consultant said, well, the reason why calcium chloride isn't accurate is because it overdries the concrete. Well, that's nonsense, because it has what's called a higher critical humidity threshold. The alkaline salts have a higher, the calcium chloride has a higher humidity threshold than either the alkaline salts. The calcium chloride in these test devices, it will try to get the relative humidity down to 18%. That's its critical humidity threshold. It's 18%. It'll start attracting water and will hold on to water 18%. So if the moisture is up, the relative humidity is higher in these air spaces, it's trying to get it back down to 18%. And that's how calcium chloride is used in closets. They put a bag of calcium chloride in a closet and it's trying to dry everything out. And that's why it keeps things from getting mildewed. There's no difference. That's exactly what it's doing. That's a passive effect. So when people hear, well, it's vapor emission, they think it's water vapor freely coming out of the concrete. That's not true. All it's doing is trying to balance the environment within that lid.
It's pulling the moisture from the air, and it's collecting on the surface of the concrete because of the salt that's inside the concrete.
Exactly. And that's one of the chief causes of slab sweating syndrome. When you get older concrete, because older concrete tends to collect a lot of the salts at the surface. So when the relative humidity gets to around 75 or 80, it looks like somebody took a shower. The concrete's wet and it dried out.
So that's a sign that your concrete has a high alkalinity.
Yeah, towards the surface. Correct.
Okay.
And here's the thing. Calcium hydroxide, which is a byproduct of cement formation, has a critical humidity threshold of 12%. It can get soaking wet and will not release water to the calcium chloride until it hits past saturation point, where where it has excess water, where it's enough to produce a relative humidity above 18%. Then and only then will the calcium chloride begin to capture that. So that's what it measures. And you can't measure what is actually captured in the calcium hydroxide, but it will capture anything that's in excess that isn't captured within those ranges. What will happen, you'll get a different reading because calcium hydroxide gets more soluble and gets colder, so it grabs onto the water more readily. But as it warms up, it starts releasing the water because it becomes insoluble. So it starts losing the water. So if you run a calcium chloride test on the same exact concrete, if it's 80 degrees, you're going to get a different reading than, well, it's 60 degrees. Well, there's no more or less water in there. It's just the ability of that salt under that condition to capture the water. That's where we're getting into the sodium hydroxide. That's the bad guy. That will start capturing water at 9% relative humidity. Even if it's desert dry, it can get wet and stay wet in really, really low humidity environments. And that's what's in the concrete, and that's what's interfering with the top surface of the concrete. And it is I'm absolutely positive that's what's causing the self-desiccation that we're seeing now, because there's not enough moisture available for the cement formation. And the reason why that happens, when the cement is initially initiated, it uses up some of the water. Well, now that they have limestone, all these other little particles in there, to properly dampen those are actually competing against the clinker to form cement. It wants water and wants to get wet. The clinker wants to get wet, but there's only so much water to go around. So what happens when the clinker absorbs some moisture and forms cement, it drops the moisture level. When you drop the moisture level, that raises the alkalinity. And when the alkalinity gets raised, it lowers the relative humidity in the surface of the concrete, because that's the most susceptible area. So for example, if it gets to 20%, the relative humidity in that area where the sodium hydroxide is 20% concentration, the relative humidity will drop to 78%. Well, people say, well, that's no big deal. Yeah, it is a big deal, because at 80% and under, cement formation stops. That water is no longer available to the cement. If it's not available to the cement, you get a more porous, permeable surface. And that's what we keep doing. So even if you put water on top, it will not allow the water to penetrate.
Right.
Because it's now in an equilibrium. As things keep going south, because what puzzled me at first when I saw some of these global studies, there was one in Portugal where it was showing that in the first 2 to 3 weeks after the concrete was placed on a roadway and also a bridge deck, the relative humidity was dropping between 50 and 70%. And they were trying to blame that on the cement hydration. So there's not enough cement in there to create that kind of a condition. It won't use up that much water to drop the humidity. So there's got to be something else. So then when I started looking at calibration salts and everything that salts do, that gave the answer. And if you look at where they have sodium hydroxide in bulk, where they ship it at 40%, that's typical, 40% concentration in water, they have to keep it heated at 70 degrees, because here's another strange property. Sodium hydroxide, as it gets concentrated, and here's the problem. The state-of-the-art study on concrete in NIST in 1999 said that sodium hydroxide is an antifreeze. And they showed a truncated graphic. It showed up to 20%. It would drop the freezing point of water to negative 14 degrees Fahrenheit. Well, that's true. However, it doesn't stay at that. As it gets concentrated from 20%, when it goes to 40% concentration, the freeze point of water is now 59 degrees Fahrenheit. And as it goes towards 60%, the freeze point of that water in the concrete is now over 100 degrees Fahrenheit. It doesn't want to move. It's behaving like ice. It's not freely evaporating moisture. So not only is the RH dropping, but the water now thinks it's freezing, and the water is now getting more viscous. If you get a sodium hydroxide moisture combination that gets up towards 60%, it's now got the viscosity of like a molasses. It won't move. You can't dry it out. That will damage the concrete surface, because now it's dehydrated, but it looks wet. You go, well, what's wet? Why is it cracking? Well, because that is not available to the cement. So that's why the top surface of the concrete, in the first inch, instead self-desiccate, and that will even happen in a laboratory. When Texas Transportation Institute did the study, I believe it was back in 2005, where they water cured the concrete for 7 days. When he isolated the top 1 inch of the concrete, it was a full 20% lower in compressive value than the remainder of the concrete. That shows there's a lack of strength gain. And the lack of strength gain means that the cement is not properly hydrating. But we're being told that's okay. That's always been an assumption. And that assumption began way back in the day when they had a coarser grind of cement. So we've not modernized our techniques to study the concrete properly. Because now, with concrete, it's changed dramatically since 2002 to the present day, where we don't have a track record of any particular concrete or cement mix design that makes any sense. Because the type 1 is what everything was based on, but as they started grinding it finer, concrete began to crack and warp and curl, so they started adding type 2, and the reasoning for it was it makes it more sulfate resistant. Yeah, it does, but that's kind of like hiding something out in the open. It's my opinion. That's the excuse they gave, not the reason. It's an excuse. So
where are all the salts coming from?
That occurs naturally in the aggregate, in the concrete, and it's also coming from the cement now with the cement kiln dust. Because cement kiln dust, and unfortunately I didn't screenshot it, but there was one recorded example where the alkalinity was 400% higher with the cement kiln dust than it was in the concrete than the cement without the kiln dust. So it's pretty dramatic. So with that concentration of alkalinity coupled with the initial hydration of the cement, now it makes sense why the concrete is self-desiccating towards the surface. Now, it doesn't do that in the center of the concrete, but it does that in the top surface, and that's where it's receiving all the damage. So
why is that?
That's because you got evaporation, and it's exposed to radiant heat and the environment. Because there's a lot of contributing factors, which I'm not going to get into because that's a real deep dive. But with evaporation alone and exposure to sunlight or even light, there's an acceleration of evaporation. So the acceleration of evaporation, even with a water cure, it's not cooling the concrete properly. Here's the other contributing factor is when the concrete heats up, even with water on it, heats up, the calcium hydroxide loses solubility because it's one of the few alkaline salts that gets more soluble as it gets colder and becomes less soluble as it gets warmer. The sodium hydroxide on the other side loves to get warm, loves elevated temperature, but then what it starts doing is starts capturing that water, making it unavailable for the cement. It's not available for
the cement kiln, that dust that's causing the high alkalinity, that was because of the EPA restrictions.
Correct.
Right.
That was a requirement. Yeah.
So it's not releasing that dust anymore, and that's dropping down into the cement. Is that right? Do I have that right?
Basically, with the more alkaline cement, it gets to that point very quickly. The cement hydration isn't as complete as it used to be. So we've got a really a cascade effect on what's causing the damage in the surface of the concrete. It's temperature, along with the insolubility of the calcium hydroxide and the increased concentration of sodium hydroxide. That's why alkalinity is so important here. Now, they keep mixing up high pH with high alkalinity. High pH is a concentration, is not concentration, but it's the strength of a salt. Now, sodium hydroxide is the other curve that it gives us is that it's really buffered. If you can have a difference of 20 times higher alkalinity and virtually won't change with the pH strip or any other pH device for that matter. So I experimented with this on a case I was brought in where I suspicion there was an sodium alkaline salt in the concrete, and where it was severely damaged, I did what I call a relative alkalinity test, where I did the normal pH test, but what I did is I put a ring of plumber's putty down and 0.5 milliliter of water, of deionized water. Then I put the pH strip in, and the area of no damage, a moderate damage, a severe damage, all measured around 11, but the severe damage was up around 12. So I added more water to the area that wasn't damaged. As I added water to it, it quickly dropped down to a pH of 9. The moderately damaged area, when I added the additional water to it, another 0.5 milliliter water, the pH didn't change. Then I did it again. It started to lower. I did it again. Between 5 and 6 times of adding water, it finally went down to 9, because that's basically concrete when it's neutral. When it's fully carbonated, it should be around 9. But the severely damaged ones, there were areas I added where it started to overflow and I couldn't add anymore, and the pH is still 11. Well, that's alkaline. The other one's it's a high pH, but it isn't alkaline. The alkalinity and the damage corresponded with each other very, very closely. But just plain concrete, it will dry it out and will crack it. It will cause warping because it responds now more to heat than it did if it stays wet. Because if it stays wet, at least it's swollen, but it won't stay wet. It captures that. So we keep going round and round this technical hamster wheel where people keep doing the same thing over and over again. And what really is annoying to me is I read these labs tests, it is assumed that, and then they come to a conclusion. You can't come to a conclusion if you're making assumptions. Because what if any of those assumptions are incorrect, which most of them are? Well, your conclusion is wrong. Most concrete studies are not correct. At least 90% of the ones I've read, and I'm being generous here, are incorrect.
Yeah.
So go ahead.
What's a sign of high alkalinity? How alkalinity, the sign of what happens to the concrete itself, other than that the salts draw the moisture from the air, and you can see it on the surface of the concrete. What are other things that is a telltale sign?
Well, I'm going to be stepping into a landmine here, but here we go. A good example is any precast concrete, because they heat cure the concrete. Now, the center portion of the precast is really, really dense and durable, because what water does, it wants to move from warm to cold. So as you're heating up the skin of the concrete and heating up the concrete, it's pushing towards the cold center. But the poor skin of the concrete is now dehydrating. Now, the way you can look at it is I've taken just plain standardized concrete, poured in place, and I've taken precast side by side. I'll put water on the standardized concrete. It'll absorb a little bit, but it takes a while. But if I put it on the precast, it disappears. Put some more on the precast, it disappears. Put some more on the precast, it disappears. I've typically seen 5 times greater initial absorption with precast than I do with standard concrete. That's because they heated it up. The calcium hydroxide and the cement formation got retarded. So when I looked at the study conducted by ACI with all these different inputs from the 1940s through around 2005, it showed that the higher the temperature, the better the compressive value was at 28 days, but the weaker the concrete was at 365 days.
Right.
That correlated with what we're seeing with alkalinity. Because if you add everything else in, the only thing that makes sense is alkalinity. At 120 degrees, they were showing that the concrete at 28 days had 200% of its targeted 28-day strength. But then when they put it in a chamber at 73 degrees, 100% relative humidity for the remainder of the full year, when they got to 365 days, the concrete was 73% weaker than the targeted value.
Yeah, that's compressive strength, right?
Yeah.
Which we've preached on this show many times that shouldn't be your measure of durable concrete. So what you're saying is the precast concrete has a more porous surface than a cast in place.
More permeable. There's a
permeable.
Difference. Yeah.
Permeable. I'm using the wrong term. Permeable.
See,
which is
And the labs do that too. I'm so glad.
Okay.
I'm going to jump in here. I'm so glad you brought that up because I saw a professor giving a presentation where he showed this curve for the water cement ratio and a reciprocal curve for what he was saying was permeability. Well, I didn't want to embarrass him, so I waited till after the class was over. I said, what you're actually showing is a porosity curve, not permeability. He thought they were the same thing. I said, no, porosity is absence of mass. Permeability is the ability to absorb something like a gas or a liquid. What I use is a desktop. I'll get this vitrified pumice stone, which was really porous, looks like a big sponge. You pour water on it, but it's somewhat hydrophobic, so the water sits on it, doesn't want to penetrate. Then I'll take a saltillo tile where there's no apparent porosity at all. You pour water and it disappears. That's permeability. That's porosity. That's permeability. There's a difference. And they keep mixing the two up. So they mix porosity and permeability, alkaline, high pH. We keep mixing these terms. And when we keep mixing these terms, no wonder people are confused.
Yeah. So this is good. So porosity versus permeability, which you define the difference is porosity.
Absence of mass.
Yeah. Is that worse or same?
But
Or
if there's
different as
there's,
permeability? If you were like, if I have to have concrete that has high porosity, I'm struggling just saying that, or high permeability, which one are you following what I'm asking?
yeah, I would prefer the high porosity unless it's in an area where there's water pressure. Then water will push in and get much greater volume. But under normal circumstances, like a roadway surface, a bridge structure, or floor, you do not want a permeable surface because it absorbs water and it transports things in and out of the concrete. Because water's fine as long as it doesn't move. If you could keep concrete underwater permanently, so for example, if you take a 3,000 psi concrete, leave it underwater and test it 50 years later, it'll probably be up around 12 to 13,000 psi. But if you move it to the tide line and you look at piers, where's all the damage? At the tide line, where the water goes in and out. The more movement of moisture you have and the more allowable moisture over time, that will damage the concrete. So porosity and permeability are both bad news. We can produce concrete that doesn't have either, but we're not being allowed to because all we have to do is hit the compressive value standard. That doesn't tell you anything because I better not say which. It was a military base, and I went to this military base and they had this roadways of, my God, look how durable that is. Well, they couldn't use it. The reason being is they had all these shredded tires and everything else in there. And they said, well, it didn't match our minimum. It didn't meet our minimum compressive value. Yeah, but the roadway is holding up. The other ones are falling apart. But we don't have a choice. Our hands are tied. Seriously.
So they could see it, like actually see it. There's a roadway that had hit the compressive strength that was specified. And then the one that didn't was actually performing better. Yeah.
Yeah. Yeah.
Well, if they weren't allowed to use it, how did they know that the one that didn't hit the compressive strength was doing better than the other? Is it the other one was just falling apart and the other one was?
Well, everything around it was falling apart. They did an experimental test section, but it didn't meet their minimum compressive value, so they rejected it. But there it is, holding up year after year. That pavement was about 20 years old when I saw it. And there was roadways around it that were less than 5 years old that had extensive damage from frisson.
That met compressive strength.
Yes. And exceeded compressive values.
Mm-hmm. Okay. I'm trying to piece this together. So high alkalinity can cause high permeability.
And high porosity.
And high porosity.
Yeah, okay. Because the cement formation doesn't occur. So what replaces it? Water. Because the alkalines capture that water and it's sitting there in place. And if you do a cross-section where this has happened, it's really obvious because you see the first inch is full of these little holes and pores, and it gradually dissipates as it gets deeper into the concrete.
Right, yeah.
Now, if it was properly cured and we controlled the water, such as with an internal curing, it should be the same all the way through. Because the goal is, if the water gets in, we're going to have problems. If the water doesn't get into the surface, we can get rid of the problems. It is really that simple. But we're not being allowed to do that because the only requirement is how much load will this bear?
Right. Well, couldn't you just solve the problem by putting a sealer on it?
No,
Why is that?
because the sealers will wear out. And also they don't have, for the most part, they actually can create more problems because with the free porosity and permeability of the concrete, you can get an alkaline buildup behind them. That salts come in, and the salts have considerable hydraulic pressure. For example, if you have etringite or like a potassium sulfate or something like that, if it goes through wet dry cycles, it'll just break the concrete underneath the sealer. If the sealer is a real strong sealer, if it's a water repellent, you may end up getting what's called self-fluorescent spalling damage. And so those never work in the long run because they always wear out because they're organic in nature. Concrete should not be treated with an organic material. It should remain completely inorganic. Yeah, but again, they don't think outside the box. They look at look at that. It's protected. Well, yeah, for the time being, but at what cost? Because if you look at ASR for floors, ASR can get triggered by the application of an epoxy resin. Whereas if you left it alone, the ASR wouldn't trigger because the ASR needs alkaline and moisture and a medium, which is your amorphous aggregate to create ASR. But if you don't trap the water in there, there's generally not enough to trigger the reaction unless it's like a polished surface.
Can you
get a dense
remind
surface.
everyone what ASR is? Or
It's Alkali-silica reaction. It's actually alkali aggregate reaction because there's other aggregates that can react as well. They're now apparently seeing an uptick in AHCR, alkali carbonate reaction with the limestone. So we're jumping into new territory and creating some more problems.
Gotcha. All right. So I think we've defined alkalinity. Do you want to talk about how to prevent high alkalinity today, or is that not something we can talk about in a short amount of time?
No, that would probably take a series to do that because
Okay.
depends because these are regional and I've offered to the different cement producers, look, I'll sign an NDA, but let me know what kind of alkalinity you have. And also the other wild card in this, because we don't know what it's doing, are the cement grinding aids. We don't know what happens to those when they're exposed to high alkalinity because it still meets the compressive value. And these grinding aids are amine-based and glycol-based. Now, they're not supposed to migrate, but they do because that information got out in this one study and they've been scrambling around trying to cover up saying, oh, no, that didn't really happen. That was something else. No, these things migrate. It says, the moisture migrates to the surface of the concrete because of the heat. Well, no, it doesn't work that way. If it's migrating towards the surface, that means it's containing a chemical that's activated by heat. That's not the water moving. It's something else that's moving. Because they said, it's moisture, the moisture is moving through. I said, no, it's not. That's called diffusion. So if something's dirty and there's a place that's clean, it wants to go from dirty to clean. That's the way it works. It's really that simple. So when the salts get more active, when they're warm, it wants to move towards the warm side, and it brings the water with it. It's not the water bringing that; it's bringing the water with it. So it's kind of a dual whammy here. And again, it is not being studied. And if it's not being studied, we're not going to figure out how to fix it. And I keep asking these laboratories, would you please start looking at alkalinity? And they're not doing it. That will fix so many issues if we start addressing that. If we can consume the alkalinity, but here's the other one too.
You think they're not doing it because there's no money in it?
I honestly don't know.
Okay.
Some of it I believe is intentional, and some of it I believe is just because this is the way they've always done it.
Right.
Because I was caught in that trap for a long time. And then when I realized almost everything I learned about concrete was wrong, at first I was upset. Then I got intrigued. Then I realized, I was part of the problem too, because I was telling everybody the same bullshit that everybody else was.
Right.
That's not the way it is. The real world, this is what happens. Because we're dealing with kinetics here. We're dealing with influences that you can't capture in a laboratory. And it's like, I was helping this one company where I was doing some consulting for. They literally had a waterproof concrete. Water did not move through it. It had no connecting capillaries, but it was being flunked by the architects because the RH was too high. I said, the RH has nothing to do with water volume. Because he said, what do you mean it has nothing to do with water volume? I said, if you take a cubic meter of space and you want to fill it up with water, it takes a little over 264 gallons of water to fill it. But if you want it to get to 100% relative humidity, you need less than 2 ounces of water. So don't tell me this 100% relative humidity is a big deal, because it's not. It gives no indication as to water volume. But they couldn't do that. So what I did is I took my knowledge of salts, and I had them add a salt, a very inert salt, to their concrete mix design, and we were able to engineer it to hit between 80 and 85%, which is what the architect wanted. The water content was exactly the same. We just add a little bit of salt to it. I mean, how stupid is that? We have to modify the concrete to meet a standard that doesn't make any sense. But that's because everybody told you it does make sense. The humidity is really deadly and all that, blah, blah, blah. I said, okay, then explain this to me. The National Association of Home Builders in the United States have stated there's over 148 million residences in the United States. Over 70 million of those are built up over slab on grade, and the slab on grade will try to reach equilibrium, and they're making that the big scary issue with RH. Once it goes into equilibrium after you put the floor down, disaster is going to happen. Oh, really? Then there should be some correlation. There should be like 50, 60 million failures. There's a few thousand, but not millions. There's a few thousand. And so that means it's something else. So we're being herded into this fenced area of non-science, I call it nonsense non-science, that doesn't make any sense. But everybody's trapped there because they're afraid to ask questions because they don't want to look stupid. Well, I've never been afraid of looking stupid. I've done that all my entire life. And I will ask questions.
I do it multiple times a day. All right. Well, I think we defined alkalinity, and yeah, we'll bring you back. I know we got a lot to talk about. Is there something that you have coming up that you want to plug? I know you just did a talk a couple weeks ago with the Moisture Mob. Is there anything else coming up?
Well, I'd like to do a follow-up on this and the 4 different common properties of water, because everybody's familiar with water's a vapor, water's a liquid, water's a solid. But there's 2 more forms of water that are in concrete that are not being addressed. That will tie in with what we've just covered here with alkalinity. And once that tie-in is given, people understand why moisture moves the way it does. And then once you understand why moisture moves the way it does, now you've got the tools to start to controlling it. That's why I didn't want to take a dive into that area, because that needs its own coverage, its own part.
Perfect. All right. Well, we'll do another episode on that. That's perfect. I appreciate it. Thank you, Bob, for coming on the show today.
Well, thank you for having me.
Yes, sir. It's always a pleasure. And folks, until next time, let's keep it concrete.
Thanks for joining us for another episode of the Concrete Logic Podcast. If you got value from the show, here's how you can provide value back to support the show. Visit concretelogicpodcast.com and click the donate button to send value back. All dollar amounts are truly appreciated. And now, to close out the show, here's Mike Dunton.
That alarm always sings couple hours before the sun comes up. Open up the side, put some diesel in the lights, and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for a dollar, give thanks to the Lord above. Never make a man do something you can't prove. Hard work calls for a drink or 2. Expect more, it's written in our blood. With wood, iron, and mud. Working hard to get